Dear student, welcome to my channel. Topic of this video is bottom-up parser. In this video, I am going to explain PCFG parser, which is nothing but probabilistic context-free grammar parser, and this is used to overcome the problem of CYK parser. To understand this video, it is very much important to understand the CYK parser. Then only you can understand the PCFG parser. Now let us start. Problem with CYK parser. How we can differentiate between the multiple possible parses of given sentence. The goal is to select the parse tree that represents the best intended meaning. Possible solutions: delegate the task to the semantic processing. And second, implement a probabilistic model to evaluate and rank the possible parse trees based on their likelihood and choose the most probable one. By assigning the probabilities to grammar rules, we can create such a model. So this is nothing but the PCFG, where we are using the rules same as CYK, that is all the rules are in CNF format, and after that we are assigning probability to each rule. So probability works as a weight factor. The PCFG is the most widely used probabilistic grammar framework, enhancing the traditional context-free grammars by attaching a probability to each rule. PCFG parsers are used in natural language processing to parse a sentence and determine their most likely syntactic structure. PCFG parser is an extension of traditional context-free grammar where each production rule is assigned a probability. This probability represents the likelihood of using a particular production rule in the derivation of sentence. PCFG consists of set of production rules similar to CFG, but each rule is assigned a particular probability. The sum of probabilities of all rules with the same left hand side non-terminal equals to 1, but this is not the compulsory rule for every time. So this you will come to understand when we are solving the problem. Parsing process. The parser generates the possible parse tree for a given sentence. It calculates the probability of each parse tree by multiplying the probabilities of the production rule used to generate the tree. The parse tree with the highest probability is chosen as the most likely syntactic structure of the sentence. Now, how the probabilities are assigned? We are not assigning the probability, we are directly working with the rules in which probability is already assigned. But how the probabilities are assigned? The probabilities can be assigned to production rule based on their frequencies in a corpus text. For example, if a non-terminal A has true production rule, A is given B and A is given C, then the probabilities can be determined as the count of A given B divided by count of A. That is nothing but the probability of A given B. That is nothing but how many times that count A and B appear simultaneously in the corpus divided by how many times A appears in the corpus. So these formulas are very much similar to the support that we used in frequent pattern. Now this is the example. So from S, NP, BP and VP, two ways are possible. So if we see the probability 0.9, 0.1. So for S it is 1. NP is two phrases are there, either determiner N or M. So 0.8, 0.2, that is nothing but 1. But this is not compulsory that left hand side summation should be 1. Sometimes it differs. Now we'll see the two examples. The first example is very simple. Statement book. Now here as a human we can easily find out that there are two possibilities are there, but correct one is that first should be the verb and second should be noun. But when we apply the CYK parser, at that time we are getting the two start symbol. One is first book is a verb and book is noun, and second book is noun and book is verb. But the first possibility is correct. So with PCFG we are finding out which is the correct tree or correct parse tree for a given statement. Now here, similar to CYK parser, we can write down the terminal book. Now book can be noun, book can be verb. Book can be noun, book can be verb. It is nothing but the probabilities. So when we are finding the S1 and S2, there are four ways can be possible. Noun, but noun cannot lead to the start symbol. Then noun verb, yes. Verb noun possible, and verb cannot lead to the start symbol. So that's why we are using only two combination. So we are using noun verb and verb noun. So with noun verb we are getting the answer 0.0036, and with verb noun we are getting the 0.0056. So if we see the value, the 0.0056 is greater than this value, so this statement is more probable. So first I will explain from the diagram, and after that it is very much easy to understand here. Now see, we can get two parse trees if we apply the CYK parser, one with the noun phrase and verb phrase, and one with the verb phrase. For example, see first book. So book treat as a noun, book treat as a verb. The book as a noun, the probability is 0.1. Book as a verb, the probability is 0.2. We never assign the probabilities to the terminal. We assign the probabilities to always non-terminal. So it is 0.1, 0.2. From the verb it will goes to the VP phrase, and for VP to verb it is 0.3. So this is 0.3. Noun to NP phrase it is 1.0. And when we form the grammar NP with VP, we are getting 0.6. So when we multiply all this, we are getting this value. And another parse tree can be possible from the only verb phrase. S to VP, VP goes to verb, verb to NP, NP to noun, noun to book. But from bottom to up, what we are doing, first book is we treat as a verb, here we treat as a noun, but the next possibility is that first book is a verb, the point to probability, book noun 0.1. From noun we can form the noun phrase which is 1.0. From the verb book to verb 0.2, then we are forming the phrase that is verb NP, which has the possibilities which has the probability of 0.9, and when we form the start symbol from VP, we are getting 0.4. So if we multiply all this probability, we are getting the answer 0.056. So this is the more probable one. And also when we are saying book should, first word should be verb only, and then it should be followed the noun. So here the same thing is represented, only this is in this way they have taken, that is from noun, verb, then NP, VP and S. So either you can represent here or you can represent in the graph also. Now the second example, a pilot likes flying planes. In my previous video I have already explained this example, so with the CYK parser, so I am not going to explain the example here. So you have to understand the example, then only you will come to know what is the calculation here is presented. Now rules are given, but rules are assigned to the probability. So these rules are assigned to the probability. Now you can see that NP, the summation is 0.7. So not necessarily the summation on the right hand side should be compulsory of a 1. So total noun phrase it may comes as a 1. Now here these are the terminals. A pilot likes flying planes. So A is determiner, pilot is NN, then likes is VBZ, flying can be VBG or JJ. I have already explained the example, so I am not taking again the example. So these are nothing but these possibilities. Now from DT NN we are creating the NP. From VBG JJ and NNS we are creating these possibilities. So we are 1 minute. Now first we will create the noun phrase, that is nothing but from DT and NN. So DT the 0.3, 0.1, and that whatever that noun phrase created, its probability is 0.3. You can see from this probability DT and NN, DT is 0.3, then NN is 0.1, NN that is going to the pilot 0.1, then when NP phrase form with the DT NN, its probability is 0.3. So when we multiply all this, we are getting 0.009. So here in graphically it is very easy to understand. For example, a pilot, A is DT, pilot is N, pilot is NN, this is not NT, it is NN, and after that DT probability is 0.3, NN probability is 0.1. They form a noun phrase and that probability is 0.3. So we are getting this calculation, that is 0.009. Next we are getting the two ways there. One is NP phrase and VP phrase. That's why there are chances that two parse trees can be generated. So flying planes can be noun phrase and flying planes can be the verb phrase. So here it is verb phrase form. So flying is VBG, here flying is adjective, then planes is NNS, it is a plural noun. So VBG 0.5, NNS 0.35, they form the VP phrase which is 0.1. So we will multiply this. Flying as a JJ, planes as NNS, and they form the NP phrase, and their probability, that is when JJ and NNS form, their probability is 0.4. So we are getting this value. So in this way these values are calculated. Sorry, this value are calculated. Now we will go to the next, and After that we will find out this value and this value. So here we are getting the two start symbol, one with the this combination and one with the another combination, but by checking the probabilities we can take the decision which statement is more probable. Now next we will calculate the this. So here two phrase gets created, VP1 VP2. So not necessary to give the VP1 VP2, we can use VP also, but it will create the confusion. That's why two phrase gets created. So at next level, so if you understand CYK parser, then there is no need to explain, and even you can easily understand what is going in the next phase or next level. So here we are forming the VP1 and VP2 phrase, which is nothing but NP VBZ and VP VBZ, because in previous our NP and VP gets formed and now they are combining with the VBZ. So when they are combining with the VBZ and NP, we are getting one verb phrase, and when the VP and VBZ combine, we are getting the second verb phrase. So in this way, see, this is the created, that is flying place. Now the VBZ likes gets attached, one with the VP and one with the NP. So we are just adding the VBZ 0.4 multiplying, and VP2 is already given, that is when we form VBZ NP it is 0.3, and when we form VBZ VP it is 0.1. So in this we are multiplying the probabilities. Now in the next there is no formation of rule, so this is empty, so there will be no. After that finally will be this S1 and S2. So when we check S1 and S2, we can easily find out that this value is greater than this value. So this tree is more probable than the next. So see this diagram very clearly, and how this multiplication can take place. Observe carefully. Advantages: disambiguation. PCFG helps in disambiguating the among multiple parse trees by choosing the one with the highest probability. Statistical basis leverages the statistical information from a corpus and providing more realistic and data-driven approach to parsing. Flexibility can be adapted and trained on different corpora and making it versatile for various language and domains. Disadvantage: data dependency, because assigning the probability is not an easy task, so require a large annotated corpus to accurately estimate the probabilities, which might not be available for all language. Computational complexity: calculating probabilities and finding the most likely parse tree can be computationally intensive, especially for long sentence with multiple possible trees. So in previous video I have already explained that during the parsing, that when the number of words in a sentence are increases, the number of possible chances of the parse tree are increase in exponential manner, that is nothing but Catalan number. So that is the problem. Sparsity: in cases where certain production rules are rare, the probability estimate might be unreliable, leading to the poor performance, because this is all basically all totally based on the probability concept. Discuss approach becomes inefficient for sentence with vast number of possible parses because of exponential growth and exhaustive enumeration. The number of possible parse trees for a sentence grows exponentially with the sentence length and grammar complexity. Calculating probabilities for all possible tree becomes computationally expensive and impractical for large sentences. So solution is inside-outside probabilities. Inside probabilities in PCFG measures the likelihood of generating a specific substring of sentence from given non-terminal, considering all possible derivation. And outside probability estimate the likelihood of generating the entire sentence excluding the specific substring starting from a non-terminal. And inside-outside probability consists based on dynamic programming, which will make the computation efficiently. And these probabilities help in determining the most likely parse tree for a given sentence. So in this video, the scope is up to only PCFG. but if you want to go into the detail, you can learn the inside outside probabilities to get the parser tree, to get the more efficient parser tree. That is, we are finding a very efficient solution based on the dynamic programming concept. Thank you.